Okay, so ladies and gentlemen, we're going to talk about stoichiometry. And what this involves is using the mole ratio for good and not evil. So what does stoichiometry really mean? Well, it means element measure. So we're measuring elements. And basically it's derived from a balanced chemical equation. The key is you must have a balanced chemical equation. And remember, chemical equations tell us a lot of different things. They usually tell us states of matter, how much we have. It obeys the law of conservation of mass. So along with this, it also tells us the number of moles and representative particles. Moles and representative particles. The key thing is it's just simply a recipe. That's what it is, a recipe to make the particular amount of products. So we're going to look at this particular equation. It's a chemical equation that involves hydrogen sulfide reacting with oxygen to form sulfur dioxide and water. So this is a recipe to tell us to make sulfur dioxide and water. That's it. But what do we need in order to make it? Well, we need hydrogen sulfide and oxygen in order to make it. That's the key. The coefficients here, 2 and 3, tell us how much we need of each and how much we will make. These coefficients can be represented in mole or representative particles. Now, let's refresh our memories on what a representative particle is. It can be an ion, a formula unit, it can also be an atom, or even a molecule. Okay, remember, formula units are derived as ionic compounds. Okay, and molecules are simply covalently bound. So, this equation can be interpreted in a couple of ways, and we're going to look at it from both mole and representative particles. So for mole, it's pretty simple. Every 2 moles of hydrogen sulfide react with 3 moles of oxygen to form 2 moles of sulfur dioxide and 2 moles of water. On the other hand, we can look at it from a smaller standpoint. Remember, moles measure molecules or atoms or ions or formula units so that we have tangible amounts, meaning masses we can deal with. Molecules, we can never separate just a single molecule in a chemical reaction for us in our lab. So this idea of using molecules, right, is on the small scale if we were looking at it from an individual perspective. So it takes 2 molecules to react with 3 molecules of oxygen to get 2 molecules of sulfur dioxide and 2 molecules of water. So what does this really mean to us? Well, what it means is that we can determine the amount of products we can produce from a starting amount of reactants. So if I have a certain amount of reactants, I can create a certain amount of product. On the other hand, we can determine the amount of reactants we need to produce a certain amount of product. So I'll give you a classic example. Let's say you're making cake, okay? And let's say that you want to make 4 cakes. Well, that means you're going to need a certain amount of ingredients to make those 4 cakes. On the other hand, let's say that you just want to make cake and you want to see how much cake you can make. Well, you can look in the pantry and in the refrigerator, figure out, do you have enough ingredients, and say, oh, well, I can make up to 3 cakes. Now, the big picture is this. These calculations allow us to not waste materials. Wasting materials and wasting chemicals is expensive. And if you're starting to waste stuff, as we all know, wasting costs a lot of money. And so what we want to be able to do is not to waste our materials, our resources that we have available to us. So that's why stoichiometry is so very important. So let's try a calculation here. Okay, let's look at it. And we're going to do what's called a mole to mole calculation. Okay, so the key thing here, it says how many moles of ammonia is this compound right here, will be produced if you begin with 0.6 moles of hydrogen and react it with excess nitrogen. Now, excess means that we have way more nitrogen than what we need. So here's the thing. We're starting with 0.60 moles of hydrogen. Okay, everyone got that? That's what we're getting. Now, here's the thing. What is the ratio in our recipe from hydrogen to ammonia? So we got to look at our balanced equation right here. Look at our balanced equation. For every 3 moles of hydrogen, I will produce 2 moles of ammonia. So, this is stoichiometry. We're using dimensional analysis. So whatever unit is here goes down here in the denominator. We're converting our moles of hydrogen into moles of ammonia. Now, we just agreed that, or I shouldn't say we agreed, I told you that there's 3 moles of hydrogen for every 2 moles of ammonia. 3 moles of hydrogen for every 2 moles of ammonia. That's our recipe. So therefore, in our recipe, our moles of hydrogen are going to cancel out. So it's basically 0.6 times 2 divided by 3. So it comes out to be 0.4 moles of ammonia. That's how much ammonia we will produce if we start with 0.60 moles of hydrogen. So we figured out how much product we have that we can create from a reactant. Now this is a pretty simple reaction because we're just going from mole to mole. But it can get more complex. Let's try another. So here we have the exact same chemical reaction as before. The nitrogen reacting with hydrogen to form ammonia. Now for this one it's different. It says calculate the number of moles of ammonia produced by reaction of 6 grams of hydrogen with excess nitrogen. Now, what's the only thing that has changed from the previous problem? Exactly. Instead of us getting given moles, they've given us grams. That's all they've done. Now, remember, everything in the class, we need to think mole. Think in the unit of the mole. Mole is the way we measure everything. So, we start with what is given. 6.00 grams of hydrogen. Start with our 6 grams of hydrogen. Now, we need to think in the unit of mole. Why do we need to think in the unit of mole? It's because each one of these coefficients is in the unit of, guess what? Oh, dare I say it, mole. Mole, mole, mole. So, we need to convert our grams of hydrogen into moles of hydrogen first. That's the key. Converting grams of hydrogen into moles of hydrogen. So in order to convert grams into moles of a particular compound, where do we need to look? Exactly, the periodic table of elements. So we look and we find that the molar mass of hydrogen is 2 grams for every 1 mole. Now, if I do my math, my grams of hydrogen cancel out. In my unit right now, I'm left in moles of hydrogen. But I don't want to know just moles of hydrogen. I want to know, with the number of moles of hydrogen that I now have, how many moles of ammonia I will produce. That's what we're trying to figure out. This is what we want to know, moles of ammonia. So in order to do this, okay, we can see here that we get 3 moles of hydrogen. So now we need to look, we need to figure out our recipe. Look at our balanced equation. So, for every 3 moles of hydrogen, we will produce 2 moles of ammonia. So, 3 moles of hydrogen, 2 moles of ammonia. My moles cancel out, so what am I going to be left with? 2 moles of ammonia is what will be produced from 6 grams of hydrogen. The key here is to remember to think in the unit of mole. You must be in the unit of mole in order to do this. Okay? Now, we can make this problem one step harder. One step harder. Can you guess what it is? Okay, here we go. Here's the last one. Look, our equation is exactly the same here. Same equation. Here it says calculate the number of, oh no, grams of ammonia produced by the reaction of 6 grams of hydrogen with, again, excess of nitrogen, meaning we have way more nitrogen than what we need. So we start with what is given. What is given here? We start with our 6 grams of hydrogen. Okay? Our next step is then to think in the unit of the mole. Mole, 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 mole. So for every 2 grams of hydrogen, there is 1 mole of hydrogen. Now we're in mole. We're thinking mole. Now in order to convert our moles of hydrogen into ammonia, we need to use our mole ratio, which is found from the balanced equation. So, moles of hydrogen, moles of ammonia. For every 3 moles of hydrogen, there are 2 moles of ammonia. Now, if I stop and solve right there, my grams of hydrogen cancel out, my moles of hydrogen cancel out, and I would be left with the answer of moles of ammonia. That's what I would have. But that's not what they're asking for. They wanted us to determine the amount of grams of ammonia. So in order to convert moles of ammonia into grams of ammonia, what do I need? Molar mass. Where do I find the molar mass? Look on the periodic table of elements. So 1 mole of ammonia. Look on the periodic table and it's 17 grams of ammonia. So the moles of ammonia will cancel out. So it's 6 times 2 times 17 divided by 2 times 3 times 1. So if we do our math correctly, it appears that we would end up with 34 grams of ammonia. How to get 34 grams? Well, 6 times 2 times 17 divided by 2 and 3. 2's cancel out. 3's just comes out to be 2. So 2 times 17 is 34 grams of ammonia. So if I started with 6 grams of hydrogen, 6 grams, it will produce 34 grams of ammonia. So let's take a quick look at the steps to solving a stoichiometry problem. The number one thing you must have, and if you don't have this, you're wasting time. You're blowing hot air. Right here, you must have a balanced equation. Next thing you have to do, you must think in the unit of mole. Mole, 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 mole. Can't stress it enough. And then you use your mole ratio. This is basically your recipe. Okay? And this comes from the balanced equation. The mole ratio. That's what it's all about. So, stoichiometry in a nutshell.